So, quick intro. I'm Matt. You can find me here on Twitter, so if you've got any other questions, just feel free to ping me. And I basically work as a back-end engineer. I've worked specifically with Go for about 3-4 years now. And at the moment, I'm working with a company called Monzo. So Monzo are a new startup. We formed the company February last year. And basically, we're trying to build a new kind of bank. And that's kind of a bit of an interesting thing to do. Banking for me is kind of like this. I don't know if anyone else has this kind of experience. If you ever go into a bank branch, they're super dated. And certainly in the UK, banking is terrible as a mobile experience. It's kind of come on the last couple of years, but you just can't do the things you would expect to do from any other kind of internet product. You can book a taxi and it'll arrive in 2 minutes. You can book food and it arrives in half an hour. But I still can't pay someone I've never paid before through any of my banking apps. I have to log into their website, set them up as a new person, and then I can somehow do that. And it's just a terrible customer experience. And a lot of the reason for that is because at their core, banks have quite dated technology. And this, for example, is the System 360. Fun fact, if you wrote COBOL or other things that ran on this, you can still run that on current IBM Z series mainframes. So that's great. You can run code from 50 years ago. But it's not really ideal if you're trying to build new products. You have these extremely large monolithic systems at the core of your bank. And lots of banks use extremely modern technologies as a kind of veneer around these things, but they can't change the core. And as an example, Barclays in the UK spent £3 billion on IT infrastructure in 2014. Who here has £3 billion to spend on IT? Anyone? One guy, cool. So just think what you could build with £3 billion. Probably something a lot better than the current banking experience. And we don't have £3 billion, not by a long way. And we're basically trying to build something that normal people would use. People who spend all their time on their smartphone and they expect very quick interactions to sort out their finances. They expect things to be automated and taken care of kind of automatically. So we started last year. We give out super fun hot coral prepaid cards. And we've basically been going through the process to become a fully regulated bank. And that kind of happened a couple of months ago. So these cards will convert into normal current accounts, probably early next year. And these are connected to an app, which is mobile first. We kind of give you spending analysis. We tell you how much you spend. For example, I've paid, James has sent me some money here, and it actually shows his profile. Really basic things like icons of where I shopped. And that's just not something that any current bank does. I don't know why. They just are unable to, and they're kind of constrained by their technology. And all sorts of other fun things. So you can do searching. You can actually search with emojis. So we look up coffee. It's a very important feature. We can attach receipts. I attach pictures of my brunch. And other things like turning your card on and off with a single tap. So if you lose it, you can, disable it. Cool, it's lost. And then you can re-enable it. Magic. And I mean, this is obviously like a bool flag in our database. But technically an enum, but that's just something that you can't do with any other bank. So if we were starting from scratch, we would obviously have some form of application. And right at the beginning, we're a startup, so we should start off really, really simple. And inevitably, we'll have some kind of application, some databases, and over time, this is going to get progressively larger. And in our case, we will need to work with lots of distributed teams because we have to integrate with lots of different systems. As soon as we expand internationally, we have to integrate with lots of payment systems, and these things get really complicated. For example, we have to have actual physical fiber delivered to physical data centers, which is kind of a bit weird. I just assumed you could put all of that stuff in Amazon these days, but that's not a thing. So eventually, these things become quite complicated. And we potentially need more databases. Our application is really big. We maybe add some searching, some caching, various other features that are essential for a bank. And inevitably, and I mean, the reason that we're kind of all in this room is that these things, like, you hit problems with them, and you actually hit them quite quickly. And I've worked on a lot of kind of big projects where we just have one big application. Obviously, we have to ship that. We have release cycles, and you just can't do anything. And so this is kind of like my impression on that. So right from the beginning, we decided we didn't want to do that. And starting out by breaking your application apart into essentially a series of microservices at the beginning is kind of a risky prospect. There's a number of things that you don't necessarily understand, and you don't necessarily kind of break things apart in the right way. But we were able to start isolating those things. So we started with a series of microservices, fairly small. These communicated via either synchronous or asynchronous message buses. And the main kind of principles behind this were, again, like standard things that we've heard from people like Netflix, Amazon, Twitter. Our services have a single responsibility. They do one specific job very well. In order to decide what they do, we take apart our whole domain and bound the context. So we have small chunks of our business logic, which we can isolate into unique applications. And then by doing that, we can build very well-defined interfaces. So for example, we can split apart our transaction model, and our transaction in my bank account shouldn't really need to know things about the merchant. Like if I buy something at a shop, obviously that has a logo, but the transaction doesn't need to know about that. We can relate those separately. And we can also, because we're doing that, we can apply different availability constraints to those. So our transactional model needs to be extremely reliable. But our kind of like merchant data, if it doesn't work, we could kind of provide fallbacks to customers, and we can kind of abstract that away. And once we break these apart, we then get really good composability. So we can break our application apart into reusable units, reusable services, and then actually we can build products much, much quicker because we can reuse some of that functionality. So when we started, we had a number of different options. And one of the things we really wanted to look at was the kind of language we would build most of these things in. In our case, we chose Go. So has anyone here used Go? Yeah, loads of people. Awesome. So for anyone who hasn't used Go, Go has a super cool, really cute mascot. This is the Go Gopher, who makes an appearance on pretty much every talk. And the thing that I really like about Go is that as a language, it's extremely simple. So there aren't a million ways that you can do things in Go. There's kind of like one way. There are other ways, but they're usually not idiomatic, and you're almost fighting against the language to do things in a different way. However, in addition to being statically typed, which for a bank is quite useful, we don't really want kind of weird type conversions and things. Obviously, rounding money is quite dangerous. Go also has a really comprehensive standard library. So although the language itself is very simple, the language comes with a huge number of tools that you can use. And as an example, the HTTP server, you can spin up a new server in about 3 lines of code. And as of, I think, Go 1.6 or 1.7, that is now automatically a HTTP2 server. So all you'd have to do is take your code, recompile it with the latest version of Go, and it will transparently upgrade your clients to HTTP2 if they support it. And that's just something that's built into the language. Like the standard library has all of these things built in. On top of that, there's a number of really cool language features. So one really big one in Go is there's extremely lightweight concurrency. And by that, I mean you can literally run any number of functions just concurrently with each other, almost too easily, to be honest. So if we had a function, for example, which is going to handle a request, this function call will block. So we'll execute that, we'll go off, and we'll kind of come back at some point in the future. Hopefully we have some timeouts if we're handling requests, and we'll assume that that's dealt with. If we want that to run concurrently, say we are in a kind of loop that is reading off a socket, and we're passing requests off to something else, we can literally just put Go before it, and that will now fire that off in a separate Go routine. And these aren't threads, these are extremely lightweight, almost like green threads, if anyone's kind of used those a long time ago. But they're extremely lightweight ways of running your code concurrently. And the reason they're so lightweight is when you fire off a new Go routine, all you're really doing is allocating like 8K on the stack. It's like really, really small. And in Go, the stacks automatically expand. So you don't need to kind of worry about that. The stack will start off really small, it's extremely lightweight, and then as your kind of stack grows, then Go will dynamically allocate memory to that. So in practice, you potentially have thousands, tens of thousands, even hundreds of thousands of these running. And Go has a really good scheduler built in. So the scheduler will basically run one operating system thread per core, and then it will dynamically schedule in user space these Go routines across those threads. And if they block on I/O, then it will kind of put that to the side, and it will schedule another Go routine so that all of them can make progress. If anyone wants to read about that, it's like really, really interesting, but probably a bit too much for right now. But the really cool thing is, like, even network I/O isn't blocking. So some of the talks I've seen before where we're using specific frameworks in, I hate to say it, Java, they're literally blocking on a thread while a request has gone to an external server. Now, that's obviously like pretty poor design, but in this case, that doesn't happen. Like, we run Go routines, we run potentially hundreds of thousands of them, and every time we fire off a request to another server, it actually goes into a separate I/O thread. And all of the networking is taken care of, and it will just kind of pass that back to the Go routine as soon as there's data to be consumed. So given that we have all of these concurrent kind of almost threads running, how do we then communicate between them? So if we need to share memory, if we need to kind of share values between these things, inevitably we're going to have to put loads of mutexes and things around these. And in Go, that's not the way that you do this. So Go advocates sharing by communicating between processes rather than sharing memory. And this is kind of based on CSP, if anyone's heard of that, communicating sequential processes, I think by Tony Hoare in the 70s. And channels provide a way that Go routines can pass messages between them. And these can be either synchronous blocking calls or asynchronous, so we can buffer them and put them in a queue. And this, again, is something built into the language, so we can literally pass messages between all our Go routines, and that allows us to do fun things like kind of fanning out, fanning in messages, we can run worker pools, and all of these things are kind of enabled and used in the standard library just by being able to run Go routines and having channels that communicate between them. On top of that, if you are building services and deploying them, Go is statically linked, or at least it is if you pass in a specific number of build flags. So by default, Go will use CGO, which uses some of the Go library, some of the C libraries available on your machine. But if you disable CGO, you can statically compile all of the native Go code, and it will then run on any machine, anywhere, well, any machine with the same architecture, without any runtime dependencies. And this is really cool if you then want to very easily deploy binaries. You can compile your whole Go program to a single file, a single binary. You can put that somewhere, you can drop that onto a machine, you can execute it, and that's it. You don't need a runtime, you don't need to install loads of stuff on your machine. So if you're kind of like want more immutable infrastructure, then this is like a really cool way to do that. So if you want to start with Go as a kind of microservice framework, there are a couple of things that you can use to do this. So one of the big ones is GoKit. I don't know if anyone's heard of this. A couple of people. So Peter Borgen, who is the kind of lead on this, is doing, I think, a workshop later this week. So if you're interested, definitely go along. And GOTOcph provides a kind of framework that allows you to build services really quickly, really simply, and you can plug in all sorts of things like service discovery and tracing and kind of all the other kind of tooling things that you need out of the box. And those are kind of all configurable in GOTOcph. There's another one called Micro, which basically is quite similar, but it takes a kind of different philosophical approach. So Micro is more of a kind of ecosystem, and as well as providing a framework that you can use to build services, it also provides lots of other tools. So there are specific discovery services that you can run, ID generation services, all those kind of things. So if you want to kind of build all those things into your system really, really quickly, then Micro provides quite a few of those. Unfortunately, neither of those existed when we started our company. So we have one called Typhon. It's available MIT licensed on GitHub. And it's basically a really kind of really simple framework. So all it does is allows us to build kind of clients and servers that can communicate to each other, and then we can configure them in a kind of standardized way. So in our case, we started off with potentially a number of services. These are communicating to each other. And the real question is how they communicate. So in our case, right at the beginning, we needed something that kind of worked out of the box really, really quickly. And one way of kind of cheating is basically to put a message bus in the middle. So if you use something like RabbitMQ, you essentially get a request queue, and you can name these request queues, and then you can have n number of instances which are going to kind of consume off that named queue. And that gives you essentially service discovery for free, because you can just publish a message to a queue. You don't actually need to know where the instances of a service are, and it will be consumed at some point by a queue. It also kind of gives you kind of, again, cheating at load balancing, because the model here is a pull model. So you have a queue of requests that are outstanding. You potentially have a TTL on those within the queue so that you don't fill the buffer. And if we have one particularly performant instance and one which has a really noisy neighbor, so we have really bad performance, then those will just consume messages at different speeds. And to be honest, that got us quite a long way. We started off in February, and we've been progressively adding more and more services to our infrastructure, building out the features of our bank, core banking systems, basically everything. So 95% of the stuff that we built is from scratch. And we've kind of started off at, obviously, 0, and we're now on about 140 or so services. So the services that we run are quite small. They do, again, one thing well, and we run a number of copies of those within our infrastructure for availability. So when we started with this, that was absolutely fine, because the only language we used was Go. And I don't know if anyone's ever had the problem where you need to do something in a particular language and you don't have any libraries for it whatsoever. Like everyone must have hit this problem. So if you're using a particularly new language, and Go is kind of getting to the point now that it's quite mature, you don't necessarily have libraries that cover every possible eventuality. And as an example, if you're integrating with financial infrastructure, you basically have to use IBM MQ. So who has used IBM MQ here? Loads of people, good. Who enjoys using IBM MQ here? Literally no one. Oh no, one person, okay, sorry. And in our case, we're trying to move fast as a startup. So writing, well, there are libraries which allow you to use those particular things, but to do that, we'd have to basically use the C bindings and compile them into our Go binary, which would be really terrible. It also doesn't have the same level of functionality, it's not as well tested, whereas using something like Java for that one specific service gives us much better flexibility. And the problem we now have is if you have built a microservice architecture and you have n number of services that are communicating between each other, you probably have some standardized way of doing this. And if you've done it all in one language, you've essentially built quite a large tool chain just in that language, which means introducing any other languages into your infrastructure becomes almost prohibitively expensive. And actually, the place that I worked at before Monzo was Hailo, where we moved from like a PHP, Java kind of infrastructure there to one that was built in Go with a couple of Java services for some specific things. And the problem we had there was we ended up with 198 Go services and 2 Java services. So we had to somehow maintain feature compatibility on these libraries, even though only a tiny amount of our infrastructure was doing that. So a quick way around that is to use a client and server that every language has, which is obviously HTTP. Bit of a stupid thing to have gone all the way full circle, but the reason that we did this was because right at the beginning, we could get all of those things like service discovery and load balancing for free, and we could write that in about 3 or 4 days. Whereas in order to jump in straight away with kind of basically HTTP-based services, you need to think about all of these kind of things. So you need to be able to discover where your instances are, which IPs they are, ports, if you're doing DNS to resolve them, or some other discovery mechanism. You need to load balance between them. You obviously need circuit breaking if some of them are slow or fail. And the real question is how you do all of this. And if you do all of that, again, in your own language, you're again building this big client and server library that do all of these things. So in our case, we chose to simplify those quite significantly. And we're actually using Linkerd in the middle to do quite a lot of these things. So has anyone seen Finnegal from Twitter? See, it's written in Scala, so it's not something we wanted to directly import into any of our services. But Linkerd allows us to run that as essentially a standalone proxy locally, and we can offload all of these things kind of into that proxy. And because lots of instances are passing through this proxy, it has a far better knowledge of what's going on in our infrastructure, which leaves our services like really, really simple. And they can still have all of the kind of performance and flexibility we need, but without having to maintain a huge amount of code to do all these kind of complicated things you need in a microservice architecture. So to start with the top of our infrastructure, we obviously have a load balancer that comes, all of our traffic goes into. We go into some kind of routing layer. So this is just going to take a HTTP request, decide where it's going to be routed to, and drop it into our proxy. And this is routed to an API service. Now, these services are no different. They essentially still just take HTTP. But what we do is we define kind of our endpoints on our API by these particular types of services. And that means, for example, we have a public API, which has a webhook endpoint that allows you to register webhooks on your bank account. And we can route all things that go to the webhooks route through our proxy into this Go binary. And then once we've done that, we can kind of process that. We're literally going to validate the request, send that on to kind of authenticate it, maybe kind of actually create the webhook and register that for callbacks at some point in the future. And these, again, have different databases. And potentially, those can kind of call out to any external provider. Literally, it's just going to be a bog standard HTTP server that's going to process our request for us. And the cool thing about this is, because all I'm doing here is deploying a new section of our API, and we have this routing automatically, if I want to deploy any new functionality to our infrastructure, we don't touch any of the other services. We can deploy services individually, we can add new services, we can add new endpoints onto our APIs without any impact whatsoever. And realistically, the worst thing that could possibly happen would be we deploy a number of instances and they consume all the CPU and memory on those particular servers, and kind of those crash as a result, and then we'd get replacements at some point. So in Go, the way we do this is by defining a type, which we call a service, and all that's going to do is take any request, so it's a function that takes a request and returns a response. So if anyone's seen anything, again, like in Finnegal, basically you pass it, you're kind of defining your service as a function. You just pass in some request, get a response back. And you allow kind of the libraries to wrap all of these kind of filters around those. And given that, we can use a bog standard HTTP routing library. So we can register routes on here. And again, each one of these, so list, register, and deregister, is again just a function that takes a request, returns a response. And it can do anything we need to do there. So this stuff's like quite easy to do in Go. You can spin up a HTTP server literally in a few lines of code. There's some really good routing libraries, and you can just register your functions straight away. So the main problem we then have as a bank is that we have to be really, really reliable. So it's all well and good having like fail whales and our services going down when it's just kind of the app that's affected. But if it's our card payment infrastructure and no one can buy anything in the store, then that's a really big problem for us. And this again is kind of the reason that we started off with this kind of infrastructure is because we need that 24/7 availability. We can't. A lot of banks in the UK have like overnight batch processes, or their systems turn off for like 5 hours overnight, and we can't really have that. We need our services to be on the whole time, and that means even though we're running in Amazon or any other cloud provider, we will inevitably have failure that we have to deal with. So in our case, we obviously everyone's using Docker because it's so hot right now. But in our case, we can actually compile our Go binary, we can statically link it, and we can put it in a scratch container. So we don't have anything inside that container at all. There's not even a shell. So if you had like a breakout, like some kind of bug in our code, there's no shell to actually execute code within that container. And we can then run those on Kubernetes. So has anyone used Kubernetes here? Cool, a few people. So from our perspective, we actually started off with Mesos and Marathon because right at the beginning, we didn't feel Kubernetes was really kind of at production level at that point. And we had kind of mixed experiences with that. We found operationally it was quite difficult to run, especially if you aren't really a kind of Java shop, which we're not. So debugging it was quite difficult. And overall, I think the Kubernetes kind of design architecturally is significantly better. Having said that, if you ever want to run it yourself on Amazon rather than using a self-hosted one, to run that in a highly available mode is still quite difficult. So there are a few blogs around that, and it's kind of a trial by fire there. But we've kind of tested our stuff quite a lot now, and it's worked out quite well. And the advantages we've seen from that is we did a kind of migration in August, so 2 months ago. And this is the expenditure on our infrastructure. So we started off with this red area, which was our old infrastructure. And we spun up our new infrastructure, and then we've kind of progressively shut things down. And the reason that we've got great cost savings here is because we can pack our services much more densely. And also we can use spare capacity for things like our compilation jobs. So we used to have really big Jenkins machines, which would like compile everything and push the resulting binaries up to S3. Whereas Kubernetes makes it really easy for us to just run those with a lower priority using spare capacity. So we don't need to run any of those servers anymore. So that's been a massive, massive win for us. So given that we have a number of instances of these services, we can use a combination of Kubernetes and Linkerd in our case, to kind of resolve things like topology changes. So if one of our services explodes in a kind of shower of flames, at some point fairly soon we'll get a replacement automatically because we've defined 3 replicas of our pods in Kubernetes. And equally, if we get slow or kind of transient errors, Linkerd will kind of resolve these for us. So internally, it's using an exponentially weighted moving average load balancer, which will detect failures, become quite sensitive to latency, and all these things kind of happen automatically. And you can build these things quite easily in Go using a host pool, and there's a couple of really good libraries from Bitly that will do this for you. But my experience is if you want to build like a microservice architecture, you're kind of putting all those things in your services is kind of the thing you should probably try and avoid. Because again, every time you want to add additional components, you then need to build an exponentially weighted moving average load balancer in that service, in that language, and you just have like a huge kind of step before you actually want to do that work. And then the other thing we do in our infrastructure is push as many things as possible to being asynchronous. So there are certain things we have to do which are synchronous. For example, if I buy something in a shop, we obviously need to check I have enough money to actually be able to make that payment. And in order for that to happen, we have to make some synchronous call through and get a response back to the card network. And that doesn't have to be too quick, but it does have to be a synchronous response. However, we use Kafka to publish events of everything that's happened in our infrastructure. And for example, if we have a service here, we would have some kind of business event, we'd publish that this has happened, and then anything else in our infrastructure can consume that. And then from these, they can then make additional synchronous requests, and if those fail, the kind of queuing system will allow them to retry with some kind of exponential backoff. The problem with any kind of infrastructure like this is inevitably you have no idea what's going on. So I might know like this section, and someone else in the company will know that section. And this is kind of something that you have to deal with if you are making calls between different services. So having well-defined interfaces, which allow you to essentially read the documentation rather than speaking in depth to different teams, is kind of really, really useful for that. The other thing that's really useful is various tooling. So has anyone used kind of tracing systems like Zipkin? No? Okay, a couple of people. So Zipkin allows you to trace a request as it goes all the way through your infrastructure, which if you have a number of services that you're kind of crossing a request boundary, that's extremely valuable because it's the only way you can really debug things like this. So Go allows you to do this really easily. So given a request that's kind of propagating through 3 services, we'd start right at the top. We, in our API, tag every request with a unique ID, which is just a type 4 UID. And then we pass that down through each request. And kind of, we basically marshal it onto the wire, send it as headers, unmarshal it in the server, and kind of pop it all the way down the stack. And in Go, we can use the context package. So Go, this used to be actually an external package, and it's recently in 1.7 moved into the standard library. So it's available built into the language. And the context package is essentially providing something like thread local variables. So Go doesn't have thread local variables. There aren't any threads. And in a context, it's basically an object that is immutable, so it's thread safe. And we can store values of any key and any value. And that allows us to store our trace ID and pass it all the way through. So we can pass that ID all the way down. And then at each one of these steps, we can kind of send off instrumentation data. And then we can aggregate all of that. We actually use a tool called Phosphor internally, but Zipkin basically does the same thing, and probably much better. And then we get all of that data into something that is completely unintelligible, like this. But obviously, this is intended for machine consumption, because we can take that and we can generate call graphs. So this is an example of a card being charged in a store. So we have our API right at the top. We have done this section that's synchronous, which is kind of the minimum things we can do to charge someone's card. We kind of need to look up the card. We have to record the transaction, update the balance, kind of things like that. And then as a part of that, we fire an asynchronous message onto Kafka, which is reliable. And nothing else happens synchronously. So in the app, you have a list of things essentially on your bank account that have happened. And at this point, that has not appeared. And it will appear at some point because we have a durable queue. But it's not essential that it appears immediately, so we can kind of shunt that off to like an asynchronous processor. And then at some point, that will get picked up, and we'll take the transaction, and we'll like look up what the company was. We'll try and get a logo for it, see if it's already got one, kind of like add as much metadata to that as possible. And then we'll fire another message asynchronously, and then something picks that up and actually inserts it into the customer's feed in their app. And then that, again, fires something asynchronously, and then at some point, they get sent a push notification, which looks something like this. And the cool thing is, here we have a coffee cup emoji, because it's a Starbucks, which is clearly an extremely important feature. But the cool thing is that all of this stuff happens, and you get this before the receipt prints out the machine, even though all of these things have happened asynchronously. But if any one of them is broken, your card would still work, and you just get like a delayed message like 10 seconds later. Or worst case scenario, if it's too late, we wouldn't send the push notification, but it would arrive. And people can still use their card, they can spend their money, and they still have a very reliable system, even though we have all this additional functionality we want to provide. In actuality, this is a massive lie. What actually happens is that. So there's lots of other things that happen. And the other cool thing is each one of these things we can aggregate log lines. So using a logging library, we have this trace ID. We can write that on every log line. We can pump that into a log aggregation system. And that means we get every log line for every one of these requests, even though they're on different servers, different services, and we can tie all of those things back together. And obviously expire them quite quickly because that's quite a lot of data. And again, you can use this kind of data to aggregate kind of maps of your systems and like really understand kind of how these things work. So why should you use Go? From my perspective, Go is a small, simple, and really easy language to learn. So we found it really easy to be able to like hire people. Obviously, hiring is quite difficult if it's a language that not many people have learned. So having the ability to pick up really easy idiomatic code has been incredible for us. And I don't think we've had anyone who's had any problems with that at all. On top of that, Go has excellent concurrency, really good communication. The networking stack's amazing. So for microservices, where essentially all you're doing is communicating over the network all the time, that's kind of like a really, really good thing to have. There are inevitably some downsides. So as I mentioned, if you're integrating with kind of some specific technologies, there might not be libraries that are particularly well tested. There have historically been problems with vendoring. So if you have dependent libraries, they obviously change over time, and you need to kind of pull all of that source code into your tree. So the way that we do that is we actually vendor every version into a single giant repository, which is pretty huge. But the advantage there is that we can vet those dependencies as they're pulled in. So we obviously have to do things like change control as a financial company, and we can vet those, and we know that that is the code that's compiled, and it's a deterministic build every time. So should you start things with microservices? Probably quite a contentious thing. I'd say the disadvantage of doing this is when we started building a company, I knew nothing about banking. And I probably still don't know very much about banking. And if you don't know a huge amount about your business that you're trying to build, then it's very difficult to make those kind of delineations between the services that you want to build. And you end up with interfaces that then change, which then causes problems. However, if you do understand your infrastructure and you understand your kind of product that you're building really well, then it's kind of a really easy thing to do. You can easily pull these services out and pipe them across, and Go is a perfect language to do that. And that's about it. So thank you very much.
So there are a few questions.
Yeah.
How do you transactionally commit events to Kafka?
So Kafka itself, we run in cluster mode, so you write to a partition. I'm trying to remember exactly how the code works. Basically, when a request comes in, we will write those into Kafka. The credit card network is kind of an interesting one because it's essentially a two-phase commit. We will get an authorization message. We will write that into our transaction database. If that fails, then we return failure back to the card network. If that succeeds, but we still return failure, then they kind of retry. And if that still fails, then 2 days later, it essentially gets undone by the card network. As far as actually going to Kafka, we write everything to a kind of partition. So you have your key will basically hash to a specific partition, and you write it straight into that. So yeah, there are inevitably failure modes. I mean, there always are in distributed systems, but yeah, Kafka kind of means once it's committed, it's definitely replicated to multiple machines.
Okay. Go, by default, has a very peculiar way of organizing source code files. How do you structure your source code and why?
Interesting. So Go stores code in packages, and essentially we would define a package as a folder with many files. As long as they all have the same package name, it doesn't really matter how they're broken up across those files, but we usually try and kind of break up, as an example, if we have a service with multiple handlers, so multiple kind of different requests that it's going to handle, each one of those will go in a different file within a handler package. And then Go provides a way to either export those or keep them internal within the package. So we would export, which you basically do by giving them a capital letter at the beginning. You export kind of a defined interface. And the default thing is to basically keep everything encapsulated unless you specifically want to export like a kind of known interface there.
Okay. How do you define transactional boundaries when multiple services are invoked within a single unit of work? And what about rollback undo if service number 4 out of 5 fails within that unit of work?
So distributed transactions, basically. Yeah, that's like not really a thing. So basically the way that we do this, specifically using Kafka for those things, is Kafka is not really a queue, it's a replicated kind of log. And that means that we define our messages very specifically. So every message has a specific schema, and we publish those. So one worker will be consuming particular messages. So if it can't process one of those messages, it basically means the entire system is down, and that consumer in the consumer group in Kafka will pause and kind of wait until we can then resume them. So in the case of the only case that really counts is where you're moving money atomically, which is obviously something that's quite important. And in that case, we do like a kind of two-phase commit in the database. And again, if that fails, our card processor that's upstream will send us a failure message, and they retry that almost indefinitely. So all I could really say is, like, if there's anything you can ever do to avoid distributed transactions, you should. I'm sure you can buy extremely expensive proprietary software for it, but there's nothing really in the open source world that will do that for you. So yeah, we basically log transactions and then kind of retry them and alert if those have failed. Is
database support good in Go? What are you using?
Yeah, so database support is actually really good. If you're using anything that's SQL-based, the standard library has an SQL driver. You can then plug in specific database drivers into that, and it gives you a standardized interface, essentially for like normal SQL databases. We actually use Cassandra, which is, because we use Cassandra for like 95% of the data that we use. There are certain things you can't really use Cassandra for, where you need kind of atomicity. But Cassandra means that we can run a distributed database. We run it with quorum reads and writes within a data center, and we route requests to the kind of correct place so that we can read and write at quorum. The support for Cassandra is okay in Go. I'd say most of the problems, most of the outages we have are probably due to that. And that's something that we are progressively improving. But yeah, kind of mixed bag.
Can you show code in Go with a microservice?
Mm-hmm.
Do you have some samples?
As in some of my code?
Yes.
Yeah, sure. Okay, let's find something good. Not really sure what's on screen, cool. Maybe not that whole thing. Cool. Okay, so let's use the webhook service as an example. Yeah, I'm just trying to find her first. Cool. Let's close all the other things I was doing. Okay. Oh, wrong screen. Yeah, that one. We have quite a lot of services, but, oh, I can't see this at all. Sorry, everyone. Okay. So if we have a look at our webhook API that I mentioned a minute ago, our Typhon library is open source, so we basically init it with a few kind of known settings. So all Go programs have an extremely small, there we go. All Go programs have a func main, and this is the entry point to your entire program. And in that, all we really do is we define a service, and then we run that service. So that is kind of like an internal library that kicks off a HTTP server. And then all our handlers are doing is each one of these, let's find list. So if you wanted to list your webhooks, which you can do via the public API, we have registered get /, which would be /webhooks/. And that is, this is kind of using a bit of a terrible compatibility layer. Probably the wrong one to have picked. This is going to take in a HTTP request and some parameters, and then it is going to check for an account ID. It's going to return a validation error. It's going to check if you're authenticated. We also pull out your OAuth client ID. And then this is the interesting part, where we use protocol buffers. Does anyone use protocol buffers? Few people, okay. So protocol buffers for us are just a way of defining essentially a message request response, and they allow you to compile that to any number of languages. So it's really cool if you want to use request responses across a number of services, and we just have our particular response type, and we make a request. If anyone wants to come and like specifically ask me this, it's probably not hugely useful on this screen, but I can walk you through kind of like a slightly more sample application.
What alternatives to Go did you consider?
Good question. So actually in our case, myself and a few other people worked at Hailo before, so we moved from PHP and Java kind of originally a kind of monolithic system to a service-oriented architecture that had kind of a handful of services and then a few more services, and then we rewrote that in a combination of Go and Java. And actually, as a result of that, Go was kind of our default choice. We did consider Ruby for a really short period of time, only because that was like super fast startup kind of get a prototype out, but that would never have been a kind of long-term solution for a microservice architecture.
You kind of suggest splitting your problem into microservices is hard. Is this not something that can be done continuously rather than upfront?
Yes, it is. So if you're starting off from scratch and you have a really, really basic product, then you probably only have a handful of services. And you can probably understand that problem well enough to break the problem apart. So in our case, we obviously have some kind of known constants, things like a bank account has transactions, so we have a transaction service. We have a number of bank accounts, so we have an account service. Equally, people have a profile with their name, address, and various other things, and those things are very easily discernible. The problem comes if you then realize you haven't quite broken it apart in the right way, and that's something that's much easier if you're doing a migration because you understand your problem domain much better than if you're building a company entirely from scratch. So it is a continuous process, and actually, on one of these slides, I think in the one where we had, no. Should have made less slides. There we go. So actually, this is a good example where we started off with a kind of a slow growth, and then we rebuilt some things and actually deleted a large section of our infrastructure. And then that's kind of gone up and down and fluctuated as we've gone up. And there have been many times where we've kind of refactored one service into a couple or deleted those, and that's definitely a continuous process.
Did you consider encapsulating the Java MQ in a Go service?
We did. However, what we've actually done is encapsulate it literally in something which will take in messages and call a specific other service, which is Go. So we have a Java service that essentially connects to MQ, and that pulls messages off, and that's literally all it does. So it's written in Scala, and it's probably like 50 lines of code. It's really, really small. And that means that all we're doing there is pulling messages off and dispatching them to another service which is in Go, which we then have all of our domain logic in. So it means it's like really nice and small and actually reusable. So if we end up having to connect to multiple different providers but with different configuration, we can actually just configure like this set of instances of that service to push data there and this one to push data there.
Okay, that's it.
Cool.
Remember to rate, and thank you, Matt.
Thank you very much.